Over 13.8 billion years ago, a profound event occurred, the Big Bang. This event marked the beginning of time, space, and everything within our universe. From a singular, infinitely small point, the universe began to expand rapidly, setting the stage for all cosmic phenomena that would follow. But what exactly happened during those first moments? How did the universe transform from a hot, dense state into the vast, complex cosmos we observe today? The Big Bang theory is the prevailing explanation for the origin of the universe. It suggests that the universe began as a singularity, a point of infinite density and temperature, and has been expanding ever since. This theory is supported by various lines of evidence, such as the cosmic microwave background radiation, the redshift of distant galaxies, and the abundance of light elements like hydrogen and helium. The idea of a beginning to the universe is a relatively recent development in cosmology. Before the Big Bang theory gained traction, the steady-state theory was popular, proposing that the universe had no beginning or end and that new matter was continuously created as the universe expanded. However, the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 provided compelling evidence for a universe that began in a hot, dense state. In the first fractions of a second after the Big Bang, the universe was incredibly hot and dense, a period known as the Planck epoch. During this time, all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. However, due to the extreme conditions, our current understanding of physics breaks down, and we rely on theories like quantum gravity to describe this era. As the universe began to expand and cool, these forces started to separate, with gravity becoming distinct first. This separation marked the end of the Planck epoch and set the stage for the rapid expansion of the universe, known as cosmic inflation. Cosmic inflation is the theory that the universe underwent an exponential expansion within the first tiny fraction of a second after the Big Bang. This expansion was so rapid that the universe's size increased by a factor of at least 10^26 in less than a second. This theory was proposed by physicist Alan Guth in 1980 to address certain problems in the Big Bang model, such as the horizon problem and the flatness problem. The horizon problem arises from the observation that regions of the universe separated by vast distances have nearly identical temperatures, even though they should not have been in causal contact with each other. Inflation solves this by suggesting that these regions were once much closer together, allowing them to reach thermal equilibrium before being rapidly pulled apart. During cosmic inflation, tiny quantum fluctuations in the density of matter were stretched to macroscopic scales. These fluctuations eventually grew into the large-scale structures we observe in the universe today, such as galaxies and clusters of galaxies. The theory of inflation not only explains the uniformity of the cosmic microwave background radiation, but also predicts the existence of primordial gravitational waves, which are ripples in space-time caused by the rapid expansion of the universe. Detecting these gravitational waves would provide further confirmation of the inflationary model. As the universe continued to expand and cool, it entered a phase known as the quark epoch, where the fundamental particles that make up matter began to form. The universe was filled with a hot, dense plasma of quarks and gluons, the building blocks of protons and neutrons. These quarks and gluons were in a state of constant interaction, but as the temperature dropped, they began to combine, forming protons and neutrons. The formation of these particles marked a significant step in the evolution of the universe, as they would later combine to form the first atomic nuclei. The strong nuclear force, which binds quarks together, played a crucial role in this process. One of the great mysteries of cosmology is why the universe is made up mostly of matter, with very little antimatter. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind only radiation. However, for reasons not yet fully understood, a process known as baryogenesis occurred, creating a slight excess of matter over antimatter. This tiny imbalance, on the order of one extra particle of matter for every billion particles of antimatter, was enough to leave behind the matter that makes up the universe today. About 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms, a process known as recombination. This marked the end of the plasma state of the universe, as the free electrons that had previously scattered light were now bound in atoms, allowing light to travel freely for the first time. The release of this light is what we observe today as the cosmic microwave background, CMB radiation, a faint afterglow of the Big Bang that permeates the entire universe. The CMB provides a snapshot of the universe at this early stage, allowing us to study its properties in incredible detail. The cosmic microwave background is one of the most important pieces of evidence supporting the Big Bang theory. It was first detected in 1965, and subsequent observations such as those from the COBE, WMAP, and Planck satellites have provided detailed maps of its temperature fluctuations. These fluctuations, which represent tiny variations in the density of matter in the early universe, eventually grew into the galaxies and clusters of galaxies we see today. The CMB also provides a wealth of information about the age, composition, and curvature of the universe, making it a cornerstone of modern cosmology. After recombination, the universe entered a period known as the Dark Ages, where no new light was being produced. The universe was filled with neutral hydrogen, and the first stars had not yet formed. However, gravity continued to pull matter together, leading to the formation of the first dark matter halos. These halos provided the gravitational wells in which gas could collect, eventually leading to the formation of the first stars. These population 3 stars were massive, hot, and short-lived, playing a crucial role in ionizing the universe and setting the stage for the formation of galaxies. As the first stars and galaxies formed, they produced intense ultraviolet radiation that began to ionize the surrounding hydrogen, marking the end of the Dark Ages and the beginning of the epoch of ionization. This period, which lasted from about 150 million to 1 billion years after the Big Bang, was a crucial phase in the evolution of the universe. Ionization made the universe transparent to light once again, allowing us to observe distant galaxies and the early stages of cosmic structure formation. Understanding reionization is key to understanding how the first galaxies formed and evolved. As the universe continued to expand and evolve, the first galaxies began to form. These early galaxies were small and irregular, made up mostly of hydrogen and helium. They were the building blocks for the larger galaxies we see today. The formation of the first galaxies marked the beginning of the large-scale structure of the universe. These galaxies formed in the densest regions of the cosmic web, where dark matter had pulled matter together. Over time, these galaxies grew larger and more complex through mergers and interactions. The cosmic web is the large-scale structure of the universe, consisting of vast filaments of galaxies and dark matter, with voids between them. This structure was shaped by the interplay between gravity and dark energy, which is driving the accelerated expansion of the universe. Understanding the formation of large-scale structure is one of the key challenges in cosmology. It requires detailed simulations and observations, such as those from the Sloan Digital Sky Survey and the upcoming Euclid mission, which will map the distribution of galaxies and dark matter in unprecedented detail. From the remnants of the Big Bang, the universe continued its transformation. Over millions of years, clouds of gas and dust coalesced under the force of gravity, giving birth to the first stars. These stars, in turn, became the forges of the elements, seeding the cosmos with the building blocks of planets and, eventually, life. In this chapter, we'll explore the fascinating processes that lead to the formation of stars and planets, the celestial bodies that illuminate the night sky and provide the stage for the drama of life. Stars are born in vast clouds of gas and dust known as nebulae. These stellar nurseries are some of the most beautiful and dynamic regions in the universe. Within these nebulae, pockets of gas and dust become gravitationally unstable, causing them to collapse and heat up, eventually forming a protostar at the center of the collapsing cloud. One of the most famous examples of a stellar nursery is the Orion Nebula, located about 1,144 light-years from Earth. It is visible to the naked eye and has been a site of active star formation for millions of years. The interplay of gravity, turbulence, and magnetic fields within such nebulae determines the formation of new stars. As a protostar forms, it continues to accrete material from the surrounding cloud, growing in mass and temperature. The gravitational energy of the collapsing material is converted into heat, causing the protostar to shine faintly. Over time, the core temperature of the protostar rises to the point where nuclear fusion can begin, marking the birth of a new star. The process of accretion can take millions of years, with the protostar eventually blowing away any remaining gas and dust with powerful stellar winds, leaving behind a young star. The mass of the protostar determines the type of star it will become, from low-mass red dwarfs to massive blue giants. At the core of a star, temperatures and pressures are so extreme that nuclear fusion occurs. Hydrogen atoms are fused together to form helium, releasing enormous amounts of energy in the process. This energy radiates outward, balancing the gravitational forces trying to collapse the star. Nuclear fusion is the process that powers stars, allowing them to shine for millions to billions of years. The type of fusion that occurs depends on the star's mass, with low-mass stars primarily fusing hydrogen through the proton-proton chain, while more massive stars use the CNO cycle. The Hertzsprung-Russell (HR) diagram is a key tool for understanding the life cycle of stars. It plots stars according to their luminosity and temperature, revealing the relationships between different types of stars. Most stars, including our Sun, spend the majority of their lives on the main sequence, where they fuse hydrogen into helium in a stable manner. The position of a star on the HR diagram provides valuable information about its age, mass, and future evolution. For example, more massive stars are hotter and more luminous, but they burn through their fuel much faster, leading to shorter lifespans. A star spends the majority of its life on the main sequence, where it fuses hydrogen into helium in a stable process. The balance between the outward pressure from nuclear fusion and the inward pull of gravity keeps the star stable for billions of years. The length of time a star spends on the main sequence depends on its mass. Low-mass stars, like red dwarfs, can remain on the main sequence for trillions of years, while massive stars may only stay there for a few million years. As a star exhausts the hydrogen in its core, it begins to burn hydrogen in a shell around the core, causing the outer layers of the star to expand and cool. The star becomes a red giant, a phase that can last for hundreds of millions of years. In this phase, the star's core contracts and heats up, eventually leading to the fusion of helium into carbon and oxygen. For stars like our Sun, this phase marks the end of their stable life. The outer layers are eventually ejected, forming a planetary nebula, while the core remains as a white dwarf, slowly cooling over billions of years. For more massive stars, the end of the main sequence is much more dramatic. As these stars exhaust their nuclear fuel, they undergo a series of complex nuclear reactions, eventually forming an iron core. Once the core reaches a critical mass, it collapses under its own gravity, triggering a supernova explosion. Supernovae are some of the most powerful events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. These explosions are responsible for dispersing heavy elements, such as gold and uranium, into space, enriching the interstellar medium and providing the material for future generations of stars and planets. The remnant core left after a supernova can form a neutron star or, if massive enough, a black hole. Neutron stars are incredibly dense objects, with a mass greater than the Sun's compressed into a sphere just a few kilometers across. They are composed almost entirely of neutrons, with a single teaspoon of neutron star material weighing about 1 billion tons. If the core is even more massive, it can collapse into a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Black holes are among the most mysterious objects in the universe, with event horizons that mark the boundary beyond which nothing can return. As a star forms, the remaining gas and dust around it flatten into a protoplanetary disk. Within this disk, small particles begin to stick together, forming larger and larger clumps through a process called accretion. Over time, these clumps grow into planetesimals, the building blocks of planets. The process of planet formation is complex and can take millions of years. The conditions within the protoplanetary disk determine the types of planets that form. In the inner regions, where temperatures are higher, rocky planets like Earth are more likely to form, while in the colder outer regions, gas giants and icy bodies dominate. As planetesimals grow larger, they begin to differentiate, with heavier elements sinking to the center and lighter materials rising to the surface. This process creates distinct layers within a planet, such as the core, mantle, and crust on Earth. Differentiation is also responsible for the formation of planetary atmospheres. Volcanic activity can release gases trapped within the planet's interior, creating a primordial atmosphere. The composition and thickness of a planet's atmosphere play a crucial role in its ability to support life. Planetary migration is a process where planets change their orbits over time, often due to interactions with the protoplanetary disk or other planets. This process can lead to the rearrangement of a planetary system, with planets moving closer to or further from their parent star. The final arrangement of planets within a solar system can have significant implications for the potential habitability of planets. In our solar system, the migration of Jupiter may have played a role in shaping the distribution of terrestrial and gas giant planets, creating a stable environment for life to develop on Earth. Giant planets, such as Jupiter and Saturn in our solar system, play a crucial role in shaping the architecture of planetary systems. These massive planets can influence the orbits of smaller planets and planetesimals, often acting as shepherds that clear out debris or destabilize the orbits of other bodies. In some cases, giant planets can migrate inward or outward during the early stages of a planetary system's formation, dramatically altering the arrangement of planets. This migration can lead to the formation of hot Jupiters, which orbit very close to their parent stars, or can scatter smaller planets into highly elliptical orbits or even eject them from the system entirely. Our solar system, with its relatively stable arrangement of planets, is just one example of how a planetary system can form. However, the discovery of exoplanets has shown that there is no one-size-fits-all model for planetary systems. Some systems have multiple giant planets in close orbits, while others have only a single planet or a widely spaced collection of planets. These differences raise important questions about the processes that lead to the formation of planetary systems. Why did our solar system develop a stable arrangement with relatively low orbital eccentricities, while others did not? What role did the presence of a massive gas giant like Jupiter play in shaping the habitability of Earth? These are questions that astronomers are still working to answer. Binary star systems, where two stars orbit each other, are common in the galaxy, and many exoplanets have been discovered orbiting binary stars. The presence of two stars can create complex gravitational interactions, making planet formation more challenging. However, stable planetary orbits are possible, either around one of the stars, S-type orbits, or around both stars in a circumbinary orbit, P-type orbits. The discovery of planets in binary star systems has expanded our understanding of where planets can form and thrive. These systems offer unique opportunities to study how planets form and evolve in different gravitational environments. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary systems by discovering thousands of exoplanets, many of which are Earth-sized and located in their star's habitable zone. Kepler's discoveries include Kepler 186f, the first Earth-sized planet found in the habitable zone of another star, and Kepler 452b, often referred to as Earth's cousin. These discoveries have raised exciting possibilities about the prevalence of potentially habitable planets in the galaxy. The sheer number of Earth-sized planets discovered by Kepler suggests that planets like ours may be common in the universe, increasing the likelihood that life exists elsewhere. The James Webb Space Telescope, JWST, launched in 2021, is poised to take exoplanet research to the next level. JWST's powerful instruments will allow astronomers to study the atmospheres of exoplanets in unprecedented detail, searching for signs of habitability and potential biosignatures, indicators of life. Future missions, such as the European Space Agency's Ariel mission and NASA's LUVOIR concept, will continue this exploration, targeting a wide range of exoplanets to study their atmospheres, climates, and potential for life. These missions will bring us closer to answering one of humanity's most profound questions. Are we alone in the universe? Finding life beyond Earth is one of the greatest challenges in science. Even if we find planets with conditions suitable for life, detecting actual life forms, especially intelligent life, poses significant difficulties. The search for life involves studying planetary atmospheres for gases like oxygen and methane, which could indicate biological processes, as well as searching for technosignatures, such as radio signals or other forms of communication from advanced civilizations. The search also raises philosophical and ethical questions. How would the discovery of extraterrestrial life impact our understanding of our place in the universe? What responsibilities would we have in terms of communicating with or even interacting with such life forms? These are questions that scientists and ethicists continue to explore. A star's life cycle has a profound impact on the planets that orbit it. As a star evolves, its luminosity, size, and radiation output change, affecting the climates and atmospheres of its planets. For example, as the Sun ages and becomes a red giant, it will expand and engulf the inner planets, including Earth, drastically altering their environments. The habitable zone around a star, where conditions are right for liquid water to exist, shifts as the star evolves. Planets that were once too cold for life could enter the habitable zone as their star brightens, while others may become too hot as their star expands. The death of a star marks a dramatic end for its planetary system. For low-mass stars like the Sun, the outer layers are ejected, forming a planetary nebula, while the core remains as a white dwarf. The remaining planets, if they survive the star's expansion, may continue to orbit the white dwarf, but their environments will be drastically different. In the case of more massive stars, the end comes in the form of a supernova, a cataclysmic explosion that can destroy nearby planets and send shockwaves through the surrounding space. The remnants of these stars, neutron stars or black holes, can continue to influence their environment, potentially capturing nearby material or forming accretion disks. Planetary nebulae, the remnants of low-mass stars, are some of the most beautiful objects in the universe. These glowing shells of gas and dust are illuminated by the dying star's core, creating intricate and colorful patterns. Although planetary nebulae are short-lived on cosmic timescales, they play a crucial role in enriching the interstellar medium with heavier elements, providing the raw materials for the next generation of stars and planets. The cycle of stellar death and rebirth is a continuous process in the universe, with the ashes of one generation of stars seeding the formation of the next. This cosmic recycling ensures that the elements necessary for life, such as carbon, oxygen, and nitrogen, are constantly replenished. Our solar system formed about 4.6 billion years ago from a giant rotating cloud of gas and dust known as the solar nebula. The collapse of this nebula, possibly triggered by a nearby supernova, led to the formation of the Sun at its center, with the remaining material flattening into a disk from which the planets, moons, and other bodies formed. The solar nebula theory explains many features of our solar system, such as the relatively flat plane of the planets' orbits, their nearly circular paths, and the division between rocky terrestrial planets and gas giants. Jupiter and Saturn, the two largest planets in our solar system, played a crucial role in shaping the architecture of the solar system. Their massive gravitational influence helped clear out the early solar system of planetesimals and debris, and their migration during the early stages of the solar system's formation may have influenced the distribution of planets. The Grand Tack hypothesis suggests that Jupiter migrated inward before reversing course and moving outward again, possibly due to interactions with Saturn. This migration could have played a role in the formation of the asteroid belt and the distribution of water-rich bodies in the outer solar system. About 4 billion years ago, the solar system experienced a period of intense bombardment by asteroids and comets, known as the Late Heavy Bombardment. This period is thought to have been caused by the migration of the gas giants, which destabilized the orbits of smaller bodies, sending them crashing into the inner planets. The Late Heavy Bombardment had significant implications for the early Earth, possibly delivering water and organic molecules that contributed to the development of life. The evidence for this period comes from the heavily cratered surfaces of the Moon, Mercury, and other bodies in the solar system. Europa, one of Jupiter's largest moons, is one of the most promising places to search for life beyond Earth. Beneath its icy surface, scientists believe there is a vast global ocean that could contain more than twice the amount of water found on Earth. The ocean is kept warm by tidal forces exerted by Jupiter, which causes the moon's interior to flex and generate heat, potentially creating an environment where life could exist. The Galileo spacecraft provided compelling evidence for this subsurface ocean, and future missions like NASA's Europa Clipper will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. The discovery of life, or even the chemical precursors to life, on Europa would be a monumental breakthrough, offering the first direct evidence that life can exist beyond Earth. Another intriguing candidate for extraterrestrial life is Enceladus, a small, icy moon of Saturn. Enceladus has a subsurface ocean beneath its icy crust, similar to Europa. But what makes Enceladus particularly exciting is the presence of water plumes that erupt from its south pole. These plumes, which were first observed by the Cassini spacecraft, contain water vapor, ice particles, and organic molecules. The discovery of these plumes has led scientists to speculate that Enceladus could harbor microbial life in its ocean, especially near hydrothermal vents on the ocean floor. Future missions may target these plumes to directly sample the water and search for signs of life. Titan, Saturn's largest moon, is unique in the solar system due to its thick atmosphere and the presence of lakes and rivers of liquid methane and ethane on its surface. Titan's atmosphere is rich in organic compounds, and the chemistry that takes place in its atmosphere and on its surface is thought to resemble the prebiotic chemistry that occurred on early Earth. While Titan's surface is too cold for liquid water, some scientists speculate that life could exist in its methane lakes, or that life might be possible in a subsurface ocean of water and ammonia. The Dragonfly mission, set to launch in the mid-2020s, will explore Titan's surface and study its chemistry in detail, searching for clues about the potential for life. The search for life in our solar system is one of the most exciting areas of space exploration. While the focus has traditionally been on Mars, moons like Europa, Enceladus, and Titan have expanded our understanding of where life could potentially exist. As we continue to explore these worlds with advanced robotic missions, we may one day answer the profound question of whether we are alone in the universe. The study of star and planet formation is entering a new era, thanks to the next generation of telescopes and observatories. The James Webb Space Telescope, JWST, will provide unprecedented views of star-forming regions, allowing astronomers to study the early stages of star formation in greater detail than ever before. JWST's infrared capabilities will enable it to peer through the dust clouds that often obscure these regions in visible light. In addition to JWST, ground-based observatories like the Extremely Large Telescope, ELT, in Chile, and the 30-meter telescope, TMT, in Hawaii, will offer new insights into the formation of stars and planets. These telescopes will have the resolution to directly image protoplanetary disks and even individual planets around other stars. While observations provide critical data, simulations and computational models are equally important in understanding the processes of star and planet formation. Advances in computing power have allowed astronomers to create detailed simulations of the collapse of molecular clouds, the formation of protostars, and the evolution of protoplanetary disks. These simulations help to test different theories and predict the outcomes of various physical processes. For example, simulations can explore how turbulence, magnetic fields, and feedback from young stars affect the formation of planets within a disk. By comparing the results of these simulations with actual observations, astronomers can refine their models and improve our understanding of how stars and planets form. Understanding planetary systems requires an interdisciplinary approach, combining knowledge from astronomy, planetary science, geology, chemistry, and even biology. For instance, the study of exoplanet atmospheres involves understanding atmospheric chemistry, climate models, and the potential for habitability. Astrobiology, the study of life in the universe, is a rapidly growing field that brings together scientists from many disciplines to explore the conditions necessary for life and to search for signs of life beyond Earth. As we continue to discover more exoplanets and learn about the diversity of planetary systems, interdisciplinary research will play a crucial role in interpreting these findings and advancing our knowledge. Black holes are among the most mysterious and intriguing objects in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape their pull. The concept of black holes arises from Einstein's theory of general relativity, which describes how mass and energy can warp the fabric of spacetime. When a massive star exhausts its nuclear fuel, it can collapse under its own gravity, leading to the formation of a black hole. Black holes come in various sizes, from stellar mass black holes, which form from the collapse of individual stars, to supermassive black holes, which reside at the centers of galaxies and can contain millions to billions of times the mass of our Sun. Despite their ominous reputation, black holes play a crucial role in the evolution of galaxies and the universe as a whole. At the heart of every black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the point of no return, beyond which nothing can escape the black hole's gravitational pull. The size of the event horizon, known as the Schwarzschild radius, depends on the mass of the black hole. Outside the event horizon, black holes can also have an accretion disk, a swirling mass of gas and dust that orbits the black hole before eventually falling in. As material in the accretion disk spirals inward, it heats up and emits intense radiation, often making black holes some of the brightest objects in the universe. Black holes can form in several ways. The most common method is through the collapse of a massive star at the end of its life cycle. When a star exhausts its nuclear fuel, it can no longer support itself against the pull of gravity, leading to a catastrophic collapse. If the remaining mass of the star is more than about 3 times the mass of the Sun, it will collapse into a black hole. Another method of black hole formation involves the collision and merger of 2 neutron stars. Neutron stars are the remnants of supernova explosions, and when 2 of them merge, they can produce a black hole. This process is often accompanied by powerful bursts of gamma rays, which can be detected by telescopes on Earth. Supermassive black holes, found at the centers of most galaxies, have a different origin story. They are thought to form from the merging of smaller black holes and the accumulation of mass over billions of years. These colossal black holes are believed to play a key role in the formation and evolution of galaxies, influencing the movement of stars and the distribution of matter. Despite their reputation as cosmic destroyers, black holes are essential to the structure and evolution of galaxies. Supermassive black holes in particular are thought to regulate the growth of galaxies by controlling the rate at which stars form. As material falls into the black hole, it can release energy that blows away gas and dust, preventing the formation of new stars and shaping the galaxy's structure. Black holes also serve as laboratories for testing the laws of physics under extreme conditions. The intense gravity near a black hole's event horizon provides a unique environment for studying general relativity, quantum mechanics, and the nature of spacetime. Observations of black holes and their effects on surrounding matter offer insights into some of the most fundamental questions about the universe. In 1974, physicist Stephen Hawking proposed a groundbreaking theory that challenged the notion of black holes as eternal prisons. According to Hawking, black holes can emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, causes the black hole to lose mass and energy over time, eventually leading to its evaporation. Hawking radiation is a purely theoretical concept, as it is too faint to be detected by current instruments. However, its implications are profound, suggesting that black holes are not entirely black, but can slowly dissipate over vast timescales. If proven, Hawking radiation would also provide a bridge between general relativity and quantum mechanics, 2 of the most important theories in modern physics. Directly observing a black hole is impossible because no light can escape from it. However, astronomers can infer the presence of black holes by observing their effects on nearby stars and gas. For instance, if a star is seen orbiting an invisible object with a large mass, it may indicate the presence of a black hole. In 2019, the Event Horizon Telescope, EHT, made history by capturing the first ever image of a black hole. The image shows the shadow of a supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of hot gas. This groundbreaking achievement was the result of a global collaboration involving radio telescopes across the world. Black holes are not immortal. Over incredibly long timescales, they can slowly lose mass and energy through Hawking radiation, eventually evaporating completely. The timeline for this process depends on the mass of the black hole. For supermassive black holes, it could take trillions of years, far longer than the current age of the universe. As a black hole evaporates, it shrinks and emits increasingly energetic radiation. In the final moments of its life, the black hole would release a burst of high-energy particles before disappearing completely. The end of a black hole's life is a reminder that even the most powerful objects in the universe are subject to the passage of time and the laws of physics. Black holes are not the only extreme objects in the universe. Neutron stars, the remnants of supernova explosions, are incredibly dense, with a mass greater than the Sun compressed into a sphere just a few kilometers across. Neutron stars can spin rapidly, emitting beams of radiation as pulsars, or merge to form black holes. Another extreme phenomenon is the gamma-ray burst, one of the most energetic events in the universe. Gamma-ray bursts are brief, but intense flashes of gamma rays that can outshine entire galaxies for a few seconds. They are thought to be caused by the collapse of massive stars or the merger of neutron stars. The study of black holes is still in its infancy, and many questions remain unanswered. How do supermassive black holes form? What is the true nature of the singularity? Can we ever detect Hawking radiation? Future observations and theoretical work will continue to push the boundaries of our knowledge. New telescopes and observatories, such as the James Webb Space Telescope and the Laser Interferometer Space Antenna, LISA, will offer unprecedented views of black holes and other extreme cosmic phenomena. As we continue to explore the universe, black holes will remain at the forefront of our quest to understand the cosmos. Stars are the building blocks of the universe, and their life cycles are a fundamental aspect of cosmic evolution. The life of a star begins in a cloud of gas and dust and ends in one of several possible dramatic events, depending on its mass. Understanding stellar evolution not only reveals the nature of stars, but also provides insight into the formation of planets, the distribution of elements, and the dynamics of galaxies. Every star, including our Sun, undergoes a life cycle that can span millions to billions of years. From the initial collapse of a molecular cloud to the eventual death throes of a star, the processes involved in stellar evolution are complex and varied. The ultimate fate of a star depends on its mass, which determines whether it will become a white dwarf, neutron star, or black hole. The birth of a star begins in a vast molecular cloud, also known as a stellar nursery. These clouds are primarily composed of hydrogen gas, along with helium and trace amounts of heavier elements. When a region within the cloud becomes dense enough, gravity causes it to collapse, forming a protostar. As the protostar contracts, it heats up, and nuclear fusion ignites in its core, marking the birth of a new star. Protostars are often shrouded in thick clouds of gas and dust, making them difficult to observe in visible light. However, infrared observations can penetrate these clouds, revealing the early stages of stellar formation. As the protostar continues to accumulate mass from the surrounding cloud, it eventually reaches a stable state, entering the main sequence phase of its life. The main sequence phase is the longest and most stable period in a star's life. During this time, the star fuses hydrogen into helium in its core, generating the energy that makes it shine. The balance between the inward pull of gravity and the outward pressure from nuclear fusion keeps the star in a stable state. Our Sun is currently in the main sequence phase, where it has been for about 4.6 billion years and will remain for approximately 5 billion more. The temperature and luminosity of a star during the main sequence depend on its mass, with more massive stars being hotter, brighter, and shorter-lived, while less massive stars are cooler, dimmer, and longer-lived. When a star exhausts its hydrogen fuel in the core, it can no longer maintain the balance between gravity and pressure. The core contracts while the outer layers expand, and the star enters the red giant phase. In this phase, the star begins to fuse helium into heavier elements like carbon and oxygen. The outer layers of the star become cooler and expand dramatically, giving the star a reddish appearance. For stars like our Sun, the red giant phase is a precursor to the shedding of its outer layers, forming a planetary nebula, while the core becomes a white dwarf. More massive stars, however, undergo further fusion processes, eventually leading to the creation of heavier elements like iron. Massive stars, those with more than 8 times the mass of the Sun, undergo a much more dramatic end than their less massive counterparts. After exhausting their nuclear fuel, the core of a massive star collapses under its own gravity, resulting in a supernova explosion. This explosion is incredibly powerful, briefly outshining entire galaxies and releasing a tremendous amount of energy and newly formed elements into space. Supernovae play a crucial role in the universe by distributing heavy elements, such as iron, gold, and uranium, into the interstellar medium. These elements are essential for the formation of planets and life as we know it. The remnants of the supernova, depending on the initial mass of the star, can become either a neutron star or a black hole. The fate of a star after its death depends on its mass. Low to intermediate mass stars, like our Sun, will shed their outer layers, leaving behind a dense core known as a white dwarf. White dwarfs are incredibly dense, with a mass comparable to the Sun but packed into a volume the size of Earth. Over billions of years, white dwarfs will gradually cool and fade away. Massive stars, however, leave behind even more exotic remnants. If the core remaining after the supernova is between 1.4 and 3 times the mass of the Sun, it will collapse into a neutron star. Neutron stars are incredibly dense, with a mass greater than the Sun packed into a sphere only about 20 kilometers in diameter. Some neutron stars become pulsars, emitting beams of radiation that sweep across the sky like cosmic lighthouses. If the core is more than 3 times the mass of the Sun, it will collapse into a black hole. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. The study of black holes, as covered in the previous chapter, reveals the extreme nature of the universe. The life cycles of stars are not just fascinating in their own right. They are also fundamental to the evolution of the universe. The processes that occur during the life and death of stars are responsible for the creation of the elements that make up planets, stars, and living organisms. The heavy elements produced in stars are spread throughout the universe by supernovae, seeding future generations of stars and planets. The energy released by stars also plays a crucial role in shaping the structure and dynamics of galaxies. Star formation and supernova explosions drive the movement of gas and dust, influence the formation of new stars, and contribute to the overall evolution of galaxies. Modern astronomy has provided us with the tools to observe stars at every stage of their life cycles. Ground-based telescopes, like the Very Large Telescope, VLT, and the Keck Observatory, allow astronomers to study stars in visible and infrared light. Space-based telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, offer unprecedented views of star-forming regions, red giants, supernovae, and stellar remnants. Missions like the Gaia spacecraft are mapping the positions, distances, and motions of billions of stars in our galaxy, providing detailed insights into stellar evolution. Observations of supernovae and neutron stars, including the detection of gravitational waves from neutron star mergers, are opening new windows into the life and death of stars. The study of stellar evolution is a dynamic field, with new discoveries constantly reshaping our understanding of how stars are born, live, and die. Future telescopes and space missions will provide even more detailed observations, revealing the processes that govern the lives of stars in greater detail than ever before. Understanding stellar evolution is also crucial for the search for extraterrestrial life. The types of stars and their life cycles determine the environments in which planets form and evolve. By studying the life cycles of stars, we can gain insights into the conditions that might support life elsewhere in the universe. The concept of an expanding universe is one of the most profound discoveries in modern cosmology. It suggests that the universe had a beginning and that it has been evolving ever since. This idea challenges our understanding of space, time, and the very fabric of reality. In this final chapter, we will explore how the universe has expanded from the Big Bang to its current state and what the future might hold. Key discovery that the universe is expanding was made in the early 20th century by astronomers like Edwin Hubble. By observing distant galaxies, Hubble noticed that they were moving away from us, with more distant galaxies receding faster than closer ones. This observation led to the conclusion that the universe itself is expanding, with space stretching out between galaxies. The Big Bang theory is the leading explanation for the origin of the universe. According to this theory, the universe began as an incredibly hot, dense point roughly 13.8 billion years ago. In an instant, it began to expand, cooling as it did so. This expansion continues to this day, shaping the cosmos we observe. During the first few moments after the Big Bang, the universe was a hot soup of particles, including quarks and gluons. As the universe expanded and cooled, these particles combined to form protons and neutrons, which eventually led to the formation of atoms. The light from this early universe is still visible today as the cosmic microwave background radiation, a faint glow that fills the entire sky. As the universe continued to expand and cool, matter began to clump together under the influence of gravity, forming the first stars and galaxies. These early galaxies were often small and irregular in shape, but over billions of years they merged and evolved into the vast structured galaxies we see today, like our Milky Way. On even larger scales, galaxies are not randomly distributed but are arranged in a web-like structure known as the cosmic web. This structure consists of vast filaments of galaxies separated by immense voids. The formation of these large-scale structures is influenced by the mysterious dark matter, which makes up about 27% of the universe's total mass and energy. In the late 20th century, astronomers discovered that the expansion of the universe is not just continuing, but it is accelerating. This surprising discovery was made by observing distant supernovae, which appeared dimmer than expected. The cause of this acceleration is attributed to a mysterious force known as dark energy, which makes up about 68% of the universe. Dark energy is one of the greatest mysteries in modern cosmology. While its exact nature is unknown, its effects are observable. It seems to be driving galaxies apart at an ever-increasing rate. The discovery of dark energy has profound implications for the fate of the universe. Depending on its properties, the universe could continue expanding forever, eventually leading to a big freeze, where stars burn out and galaxies drift apart. There are several possible scenarios for the ultimate fate of the universe. One possibility is the big freeze, where the universe continues to expand and cool, eventually reaching a state where all stars have died and no new ones can form. In this scenario, the universe would become a cold, dark, and lifeless place. Another possibility is the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, planets, and even atoms themselves. In this scenario, the universe would end in a violent and dramatic event. A third possibility is the Big Crunch, where the expansion of the universe eventually reverses, and it collapses back in on itself, possibly leading to another Big Bang. The expansion of the universe has profound implications for our understanding of space, time, and existence itself. It suggests that the universe is dynamic and ever-changing, with a history and a future. The study of cosmic expansion also forces us to confront the limitations of our knowledge as we grapple with the mysteries of dark matter and dark energy. By studying the expanding universe, we gain insight into the nature of reality and our place within it. The realization that the universe is vast and ever-expanding challenges our perspective and inspires us to explore the cosmos further. As we continue to observe distant galaxies, measure the cosmic microwave background, and study the effects of dark energy, we are uncovering the secrets of the universe and shaping our understanding of the cosmos. Observing the expanding universe requires powerful telescopes and innovative space missions. The Hubble Space Telescope, for example, has provided us with some of the most detailed images of distant galaxies, helping us to understand the history of cosmic expansion. The upcoming James Webb Space Telescope promises to push these boundaries even further, allowing us to look back in time to the very first galaxies. Other missions, like the Planck satellite, have measured the cosmic microwave background with incredible precision, providing insights into the early universe's conditions. Future missions, such as the Euclid spacecraft, aim to study dark energy and dark matter, helping us to understand the forces driving the universe's expansion. As we come to the end of our exploration of the universe, it's important to reflect on the role of humanity in the cosmos. We are a tiny part of an immense and expanding universe, yet our curiosity and desire to understand the cosmos drive us to explore, discover, and learn. Our study of the universe not only satisfies our intellectual curiosity, but also connects us to the larger story of cosmic evolution. While the universe may seem vast and indifferent, our ability to comprehend its expansion, structure, and future is a testament to the power of human inquiry. As we continue to push the boundaries of our knowledge, we are reminded of our place in the universe and the responsibility we have to preserve our planet and continue exploring the cosmos. If you like the video, please subscribe and like. It helps us grow together.